Let's go ahead and get started. Today we're going to look at the example, homework number 1. This is talking about the building system gravity. So given the floor plan diagrams below and a uniform 10 psf load, determine the free body diagram loading for each of the highlighted beams. So we have 3 green beams and 1 blue beam. And green beams are all going to be the same. If you look at those, you can tell that they are identical, hopefully by intuition, but if not, you can go ahead and work through each of them. I'm only going to work through one. So this problem looks something like this. We have 2 columns at the left side, girder. We have 4 overhang beams. We have columns in the middle, and then girder there. So the overhang beams, the green beams, all hang over the girder or the column, depending on which one we're talking about. The 3 green beams are these, green. So what we're trying to do is figure out what is the loading on those. So recall from the picture that this is uniform decking, and recall from the lecture that uniform decking creates a uniform distributed load on each of the beams that supports the decking. So in this case, the deck is supported on all of those green beams, and it's uniform across the whole length. So we're going to figure out what is the loading based on the tributary area. So let me go ahead and change the color here. I'm talking about tributary area. So we know that these spaces, there are 4 spaces, and the total is 20 feet. So each of these spaces is 5 feet. And then we can say that the tributary area for any one of these green beams is half on one side, half on the other side. We end up with an area that looks like this. So the top side is 5 feet, half of that is 2.5. So the top tributary area is 2.5. Same thing for the bottom, 2.5. So the total tributary area, or tributary width rather, is 5 feet. So we know at every point along the length of the beam, we have 5 feet of tributary width. We know that we have 10 psf loading. So if let's use lowercase p, equals 10 psf, then W, the uniform load, equals P times the tributary width, which is 5 feet. So we have 10 psf times 5 feet gives us 50 pounds per foot, or 50 PLF. Now for those of you that don't like using the tributary width, you can of course figure out the total tributary area. We know the length of that beam is 20 feet. So the total area is 5 feet. That's the width times the length is 20 feet. So 5 times 25 is 125 feet. Divide that, sorry, there was a mistake there. 5 times 20, not 5 times 25. That gives us 100 feet squared. And then we divide that by the length to give us the uniform load, or the total load, rather. We can find out from 100 feet squared times that 10 psf equals 1,000 pounds total. Okay. We divide that by the 20 feet, so we get 1,000 pounds total load on that tributary area, divided by the 20 feet of beam length. 0 cancels out nicely. 100 divided by 2 is just 50 pounds per foot. Notice that those are the same. Both methods are equivalent. Both methods work. So our free body diagram for the green beam looks like this. We have a pinned reaction at the left side where these green beams frame into the girder. So this connection is represented by a pin. Where the beams frame over the girder, We have another pin reaction. Mark it as a roller for the same reasons we talked about last semester, how if we create a pin-pin reaction, we create an unsolvable problem. We don't want to do that. So this reaction I'm representing by a roller. This beam is an overhang beam, and the uniform load on top of that beam is the 50 pounds per linear foot, 50 PLF. So the final answer for that part 1, the green beams, is 50 pounds per linear foot. Now, for part 2, we're going to need the reactions of this beam, so go ahead and figure those out. Because we've done that a lot in the first semester, and I think it's something you should know, I'm going to go ahead and not work through that, but I will give you the reactions to be 1,000 pounds and 0 pounds. Okay, so the short reason for that is that the total load we've already calculated to be this 1,000 pounds, right? We know that's the total load. We know that it acts at the center, so the equivalent concentrated force acts right here. That happens to be the same location where the girder, or the beam overhangs the girder. So the reactions are right on, the reaction and the concentrated load are acting at the same point. So they're equal and opposite and completely balanced. This left reaction is just there for stability. So 1,000 pounds at the center reaction, 0 pounds at the left reaction. Do the math. If it doesn't make sense to you, work out that problem. You're perfectly capable of doing that from what we learned last semester. So now we look at that blue beam in the center. If I go back up to the top, that blue beam is this one right in the middle. What we know is that each time one of those beams overhangs the girder, that we get a concentrated load. Here we go. So we'll have 1, 2, 3 concentrated loads. We don't get a concentrated load at the column because the overhang beam passes its load directly to the column. So we don't have a concentrated load at the end. And the last thing to note is that the deck is spanning up and down, so it doesn't pass any load to that center blue girder. So let's go ahead and draw that blue girder then. Going to end up like this. Each of the columns has a pin reaction. Just like always, I'll label one as a roller and one as a pin. So there's a pin reaction for each of those red boxes. And then we're going to end up with 3 concentrated loads on the top, 1 at each of the places where the girders overhang, the beams overhang the girders. So we have 1 at the center, 1 at the quarter point, and 1 at the 3/4 point. Now, what's the magnitude of each of those loads? Well, it's equal to the reaction from the overhang beams because that's the load that's being passed to the reaction, which is caused by the girder. So 1,000 pounds each, 1,000 pounds, 1,000 pounds, 1,000 pounds. All right, if we want to figure out the reactions from this beam, we know that this is a symmetric beam. So it's the total weight divided by 2 because the loads are evenly distributed. So we have 3,000 pounds divided by 2. The reaction on the left equals 1,500 pounds. Reaction on the right also equals 1,500 pounds. Again, you can use the equations that we learned last semester. Sum of the moments, sum of the forces y, sum of the forces x. To do all of that, we know that we do have an x equation, or I'm sorry, an x reaction. We know that it's equal to 0 because there's no loads in the x direction. But basically, we just solved that problem, figuring out the loads and reactions that pass through the building. Those reactions get passed to the columns because that's what supports the girder, and then it moves on down floor by floor. Okay, moving to the next problem. Let's go ahead and work through that. So the next problem is a little more complicated of a framing plan, but somewhat similar. So we have 4 columns again. Oops, sorry about that. 4 columns again. We have beam, girder, girder, girder in the middle, girder on the end, 3 beams here, and a beam here. Deck load spans this direction over here, and up and down over here. And we can go ahead and say that we need to first figure out the green beams. That's our first problem. So let's go ahead and shift the color to green. We're talking about one of these beams. Again, all these beams are the same. They all have the same tributary area. They all have the same length. So not too much to think about. In this problem, this distance is 10 feet. Just like the last time, that means we have 1, 2, 3, 4 spaces. 10 feet divided by 4 is 2.5. We take half of that distance from each side of the beam, so half on this side, half on this side. We end up with 2.5 total. So our uniform load is equal to, uniform load W is equal to that 10 PSF times the tributary width, which is 2.5 feet. 2.5 times 10 is 25. We have pounds over square feet times feet gives us pounds over feet. We have W equals 25 pounds per foot. So if we were to draw the free body diagram for that, we know that that's simply supported. It has a reaction on each end where it connects to the girder. I made one of those a pin reaction, one of those a roller reaction, and we end up with a uniform load of 25 pounds per foot. Okay. The length of that beam is 10 feet. Again, symmetric. So we can say that the reactions are equal. So we have our Ly, our Lx we know is equal to 0 because there are no horizontal loads. Our Ly, our Ry, both equal and both half of the total. So the total is 25 pounds per foot times the total 10 feet is 250. Half to the left, half to the right, 125 pounds. 125 pounds. Again, if that is confusing to you, solve it out. Some of the moments, some of the forces in the y direction, you'll get those answers. And that's no problem. Just make sure you feel confident in how we get that. Okay, moving to the blue beam. That's this girder in the center. So with the girder in the center, we're going to have, again, it's supported by 2 girders. So sorry about that again, I keep popping up there. Supported by 2 girders. Those girders are represented by a pin and roller reaction. We have 3 concentrated loads from the beams. So from each of these green beams, there's a concentrated load where the beam frames into the girder. So we have 3, one at the center, one at the quarter point, one at the 3/4 point. Each of those loads, of course, are equal to the reactions from the beam, just like before. So 125 pounds, 125 pounds, 125 pounds. So that takes care of the right side. On the right-hand side of this beam, the deck is spanning up and down, so it does not add any load to the girder. On the left-hand side of that girder, it does not follow that rule. The deck is spanning left and right, so it does pass load to the girder. We need to take a look at what is the tributary. So half of that space is tributary. We know that that total space is 5 feet. And half of it is 2.5 feet. Okay, so 2.5 feet times the 10 PSF is what we get for W. W equals 10 PSF times 2.5 feet. Same as before, 25 pounds per foot. So the uniform load on this blue beam is 25 pounds per foot. Uniform completely across the entire beam because the deck is running that whole distance. So we get 25 pounds per foot. Now we've drawn the free body diagram for that beam. If you want, you can calculate the reactions. I don't think that I specifically asked for that, but reaction Ly equals reaction Ry equals, we know that the x, RLx equals 0 because there are no loads in the x direction. This one also is symmetrical, so we can say that half of the load goes to each side. Again, you can get that using some of the moments, some of the forces, but I'm just going to say half. So we have 125 plus 125 plus 125, that's 375 from concentrated loads. We have 25 pounds per foot. The length of that girder is 10 feet, so we have 250, 25 times 10, pounds of uniform load. So 375 plus 250 makes 425, 625. 625 pounds. If we want to divide that by 2, we end up with 312.5 pounds on each side. So 312.5 pounds and 312.5 pounds. Those loads are in turn passed to the other girders on the top and the bottom. I'll mark those as red here so you can see which one we're talking about. But that blue beam passes its load to these girders. Those loads eventually pass to the columns in the corners. Okay, so we're done with those initial framing problems. Now we are asking you to determine the framing plan for the bank. So let's take a look at the bank. Just as a reminder or a quick note that there are lots of answers for this. So there's no real right answer, but there's a few things that you need to make sure you have done, okay? So I'm going to talk about that for a second. First of all, let me quick sketch what we have. So we have something that looks like this, a very square bank building. We have offices on the right side and a vault. 1, 2, 3, 4. Stairs up here. The vestibule out front. And then a teller station. Restrooms in the back. Okay, on the second floor, we have more offices. The same floor plan, I put a grid on there so you can see it. I mean the same size, rather. We have this corridor running here. This is open to below. Stairs up top, just like below. And then we have 3 offices, big office in the corner, and 3 more offices. So the important thing that you need to remember is that you support each piece of this bank, okay? So I'm just going to call out a few things. First of all, you probably want to put columns in the corners. That makes sense, right? Those are pretty much out of the way because they're right against the wall. And there's a good place to make sure that you have support everywhere. So those columns are going to continue up through the top of the building. So I'm going to put them on each level here. You also, so remember that this is, on the left is the first floor plan. On the right is the roof plan, and we're showing what's below. So the roof plan has to support the roof all the way through. The floor plan on the left has to support what's above it on the right. And so let me draw one more plan to help make sense of this. This is going to be the absolute roof plan. So this is the framing that's on the roof. This is not shown in the drawing, but I think it's helpful. So we have our 4 columns coming up, and there's actually nothing up there. It's just a low slope roof. So at the roof level, we want to have framing that supports the whole roof. You can do any number of situations, but probably it's going to be something like this. You have joists or beams running on the perimeter, and then you have joists or beams making that full span. That's about 60 feet. Using our rules of thumb, we can say 60 feet, 30 inches deep for that joist. That's not so bad, so I'm going to go ahead and leave it as that. We have about 14 feet 14 feet for that level, so losing that space probably going to be okay. All right, so our roof framing plan looks like this. We'll call these beams approximately 30 inches deep. This one is girder. Also somewhere between 30 to 60 inches deep. The girder gets a lot more load than the beam, so it might be closer to 60. But it's also along the wall, so it hides out, not going to cause problems with ceiling clearance. So not so much to worry about. Now let's look at the second level. So we have those columns there. Makes a lot of sense to run beams like before along the perimeter. Okay. Of the two sides where we're supporting floor, that makes a lot of sense. What we really need to realize is that we need to support this corridor, and we need to keep this area open. We don't want to run beams across the middle of that opening, or that really ruins our architectural look. So probably we need to choose, again, there's lots of choices here, but we need to choose whether we run a beam up and down in this plan view or horizontally in this plan view to support that corridor. I'm going to go ahead and pick up and down, and I'll explain that in a second here. Well, I guess there's not really a great reason to pick one or the other, so not much to explain. So I'm going to run a girder here. I'm going to run a girder across the columns because otherwise this girder that I drew along the corridor would not have a support. I need to support the edge of that corridor with another beam here. So I have that. And then we need to support the floor. So if you look at the offices, that distance is about 20 feet. Let me mark that on this drawing. So this distance is somewhere around 20 feet. And that's a really long distance. We can't span it with just a deck. So we need to put beams in there to support that. So I'm going to put beams in there. We have, let's see, about 40 feet in the opposite direction. So this is 20, and this is 40. I'm going to go ahead and put beams at something around 6 feet. So 40 divided by 6, that gives us about 7 spaces. Let's go ahead and make it, well, draw a beam in the middle. We have 2 spaces. Split that. We have 4 spaces. Split that one more time. And we have 8 spaces. So our beam framing here supports those offices. We're good there. We need to do the same thing on the other side. That side is going to be 60 feet. So we want to do really similar here. That gives us 2 spaces at 30. Gives us 2 spaces at 15. And then if I split that 15 into 3, that gives us 5-foot spacing. So these beams are 5-foot spacing typical. These beams are 40 divided by 8, which is also 5-foot spacing typical. That's good. The one thing I want you to make sure you note is that the deck spans this direction over here and this direction over here. Otherwise, it wouldn't be supporting itself on those beams. If we span the other way, it would be supporting itself on the girder, and we can't reach that far. That's too long. Okay, so that supports that second level. We got the corridor. We left the opening open. The one thing I forgot to draw on here is that this beam right here doesn't have a support on the left side. We need to make sure we put a closure girder over there between the columns. One final thing that you can only see on the bottom level is that we need to support the roof of this mezzanine. So we're going to go ahead and put 2 columns out there. Some of you might be like, why don't I just cantilever out? Well, I don't have a backspan here. So if I put my beams, out here from that girder that runs across there, there's no backspan. I can't overhang unless I go all the way through here, which would completely ruin your architectural look of that open space. So we don't want to do that. We would rather put columns out there in the corners. We're going to have to support that glass, even if it is glass. So those columns are going to hide out pretty well. Put columns out there and then span these to the roof. Taking a look at that size, it's 20 feet. So right now I have two 10-foot spaces, so let's go ahead and add 2 more beams so we have 5-foot spaces. So this framing plan would be perfect for the building. Like I said, there's many options. I did actually realize just now that I forgot the stairs, so let's go ahead and be a little more careful about the stairs. I put those beams over here right through the stairs. We need to be more cautious about that, so let's see. Go ahead and erase these. We have the stair framing that's here and here, and framing down, okay? So we want to make sure that when the stairs go up, which goes up on the outside, that we have a stringer that spans right there, and another stringer that spans from that mid-level down to the floor. And then we want a beam for closure on the outside, and then another stringer here, and another stringer here. So we end up with 4 stringers. 2 of them go up. I'm going to label those. These 2 go up to the second floor from the platform landing. These 2 go down to the first level from the platform landing. And then we need to add a column and a beam for the platform landing, which I added over here for clarity. So this is at the level of the platform, okay? So 2 stringers come from the top. If I go ahead and take a section cut of that area to hopefully help clear this up. 2 stringers come from the top. They have a platform. We go down the stairs. They have another platform. They frame into the beam that we added. This beam. These stringers are these guys. There are 2 of them. And then we have another stringer that runs here and then down to the ground, supported by a column. So this is on the ground. So there are 2 stringers that run below the platform and 2 stringers that run above the platform. These stringers up here are supported by this girder, which is right here. Okay, hopefully that makes sense to you. Like I said, there are many choices, options for framing this. Just like there are many architectural options for any building, there are plenty of structural options. So if you don't have exactly this, don't worry, as long as you make sure you support all the loads. That concludes example homework 1. If you have questions, feel free to ask me after class.